This is page 241 of the Incredibles book. We are looking at the definite integral. We've already done definite integral as a number. Now we're looking at definite integral as a function. All right, so I'm not doing all of these. I'm going to do the ones we did in class. All right, and if you have specific ones you want me to do, I can do that later on. So here, so we'll integrate like normal. So that's going to be the integral of sine is negative cosine, so it's negative cosine t, and you're going to take that from 0 to x, substitute, so it's negative cosine of x minus negative cosine of 0, so that's negative cosine x. Cosine of 0 is 1, so minus negative makes it plus 1. So f of x equals negative cosine x plus 1. That's it. I guess I'll do b. Here, integrate that. That's going to be t cubed, right? 3t cubed over 3, so the 3's would cancel. You have 4 there, x there. Substitute x cubed minus 4 cubed. So it's x cubed minus 64. That's it. I'm going to skip C. It's about the same thing. Don't worry about problems like E. If I do present later on, I'll just do it later on. Let's do G. So I'm going to do G and H, and that's the last of our examples. And the reason why I'm not doing a whole lot of these, because this is not how you're usually going to see this type of function. You're going to see it some other form, all right? So this is t squared minus 5t. Take it from 2 to x squared. Put the x squared in. Put the 2 in. So that's x to the 4th minus 5x squared. Minus 4 minus 10 is negative 6, so it's plus 6. And that's our answer. We're going to do H. H was requested in class. So integral of 1 over t is natural log of absolute value of t. Take that from 4e to the x to e to the x. So that's natural log of e to the x minus natural log of 4e to the x. Okay. Natural log of e to the x, that cancels. Natural log and e cancel. This is negative. I'm going to rewrite that as natural log of 4 plus the natural log of e to the x. Right, that's a property of logarithm. X minus natural log of, oops. I mean to distribute the minus sign, so it's natural log e to the x is x. So the x minus x cancel, giving you just negative natural log of 4. And that's it. That's the only examples I'm doing for 241. Jumping on to 242. Now, this is the second fundamental theorem of calculus. This is what I intended to do. Keep in mind, so this is the derivative notation, and that's the integral. And recall that differentiating and integration are inverses of each other. So look what does it have here. As long as you have from some constant to x, you take a derivative of the integral, you just get the inside back. The only thing is you got to take the derivative of what this function is up here on the outside. It's like chain rule. So here, I'm going to plug in the x, and it's just x squared plus 1. And that's the answer. That's it. That's the derivative of that function. All right, so here, plug it in. So it's going to be 5x minus 3. That's it. That's the derivative of that integral. C, okay, so note the way they wrote it. They want the variable to be on top. So I'm going to do this one. I'm going to flip it. So it's d dx, the opposite of, because I'm switching it, so the variable's on the bottom, I want it on top. So put x and then 7, and then 5t minus 9. And that's the derivative I want. So now it's negative of 5x minus 9. That's it. So that's negative 5x plus 9. That's it. And yes, don't worry about the 7. Don't worry about the 7. Don't worry about the bottom number. We're going to skip problems like D. If it comes up in the homework, you can admit it to. E, Let's do that one. So this is that chain rule that's needed here. Plug in the 5x squared plus 1 into t. So it's 5x squared plus 1. Now, put that in parentheses, put whatever you got out of it in parentheses, and take the derivative of what you plugged in. You plugged in 5x squared, so you need 10x. So that means that's 50x cubed plus 10x. That's the answer to E. All right, let's go to F. No, we're not doing F. The reason why we're not doing it is because we got a variable down there and we got a variable up there. I guess I may as well do it for kicks. All right, so that's d dx. And what I want to do is rewrite this as x to 0 of 3t plus 1 dt plus 0 to 2, what is that, x squared? X cubed. 2x cubed 3t plus 1 dt. Right? So remember that property where you got this number and this number are the same. Okay? But remember, our fundamental theorem of calculus doesn't allow for the variable down there. So I got to rewrite it again. So that's going to be negative of 0 to x of 3t plus 1 dt plus 0 to x cubed 3t plus 1 dt. So I didn't do anything with the second integral. I'm only working with the first integral. Now that I've got that, I can just take the derivative. Oops, since I'm taking the derivative, I don't need that anymore. So it's the negative of 3t plus 1, 3x plus 1. Remember, all you're doing is substituting that variable, substituting that function, whatever it is, into t. And then plus, now I'm plugging in 2x cubed. So it's 3 times 2x cubed plus 1. And you want to multiply that whole thing by the derivative of that. So it's 6x squared. Right? The derivative of 2x cubed is 6x squared. So let's clean this up. That's negative 3x minus 1. That's going to be 6x squared times that. So it's 6x squared times 6x cubed. So that's 36x to the 5th plus 6x squared. And that's basically it. That's it. All right, that's page 242. Moving to 243. How many times? 7 minutes? That's not bad. All right, so this was the part I wanted to get to. We're treating this as an accumulation function. We're treating the integral as an accumulation function. So in this example 1, that looks out of focus, isn't it? Is it not in focus? I don't know how to fix that. All right. So we're looking at the line f of x equals 2. So you have a line at 2. All right. And we want, this is our f of x, right? This is our f of t or whatever, all right? And we want, and remember it's a horizontal line. I know it's kind of going down, but it's pretend it's horizontal. All right, and so we want to do this thing. It's 0 to x. So if it's 0 to 0, then there's no area. 0 to 1, that's this area here. It's 1 by 2, so it's 2. If it's 0 to 2, so we'll go from 0 to 2. Now it's 2 or 2 by 2, so it's 4. And then 3, it'd be 3 by 2, so that's 6. And then 4 by 2, so it's 8. And then 5 by 2 is 10. Right, so that's the area. So at 0, it's no area. At 1, it was an area of 2. Remember, we're looking at this area. That's how we got this 2. And then at x equals 2, or t equals 2, the area became 4 because it's 2 high and 2 wide, so it's 4. All right, that's it. That's the accumulator function. So this function has the equivalency of, let's say, if you plugged in x here, and what is f of x? It's, if you plug in 0, you get 0. If you plug in 1, we got 2. If you plug in 2, you get 4. That kind of thing. So it's making that table. That's what this table was. All right, now let's look at the next one. Okay, so this time the line is f of x equals x. Again, we're doing this thing from 0 to x of f of t dt. All right, so from 0 to 0, of course, is nothing. 0 to 1, so now 1, if you plug in 1 in there, you get 1 out. So 1, but it's a triangle, so it's 1/2. Okay, so it's 1/2. So base is 1, height is 1, 1 times 1, and divide by 2, so it's 1/2. So at 2, you get 2 again. So 2 times 2 is 4. Divide by that by 2, you get 2. Then 3. 3 and 3, so it's 9 halves. 4. 4 times 4 is 16, divided by 2 is 8. So that's the function. All right, so that's the nature of the function. That's the accumulated function. And we'll see more advanced ones later. All right. But I want to talk about this real quick. Because here they're asking for the derivative, right? We're asking for the derivative. So this is not really an accumulation function practice. This is a second fundamental theorem of calculus practice. So if you plug in x, so f prime of x, that's going to be x cubed. That's it, right? Because the derivative of x is 1, so there's nothing needed here. Here, it's going to be f prime of x equals 5. Remember, taking the derivative just there, and you substitute that x, but there's nowhere to substitute, so that's just 5. Let's do 3. So that's going to be f prime of x is going to equal 4x minus x squared. That's it. Let's move on to a more interesting problem. Let's do 5. So you're going to plug in the x squared, so it's x squared cubed times the derivative of x squared, so it's times 2x. So that gives me 2. That's x to the 6th, x to the 7th, and that's the answer. All right, let's do 6. So f prime of x is sine of x squared times the derivative of x squared, which is 2x. Right? So you can leave it like that because this is not really cleaning up. You're just getting rid of parentheses. All right, that's it. Let's do 7. So f prime of x is 1 over sine x times the derivative of sine, which is cosine x. All right. All right, that's enough. All right. Now, so the homework was related to this. The homework is the next page. This is page 246. Okay, so at x equals 0, it's 0. At x equals 1, so here's 0, here's 1. I have 1, 2, 3. So that's a height of 3, right? 1, 2, 3. That's a height of 3. That's 1 here. So 1 plus 3 is 4. Times 1 is 4. Divided by 2 is 2, right? Remember, area of a trapezoid is 1/2 the height times the sum of the two bases, right? My two bases were 1 and 3. My height was 1. So for 2, so to 2, you include what you had before, which is 2, and then you add 1, 2, 3 more. So that's 5. And then the 3, this area is, what is this area? This is 3 high and 1 wide, so it's 3 halves, so 6.5. Right? Remember, I'm adding the previous values. Right? And then 4, this is 1, 2, 3, 4. It's a negative 4 down here. So if the height is negative 4, the width is 1, so it's negative 2, right? Negative 2, it's the area of a triangle, but you add it to the 6.5, so it's 4.5. And then you're going to subtract 2 more, so it's 2.5. And then you add half a unit, so that's 3. And then you add a quarter unit, so it's 3.25. And then you subtract a quarter unit, so it's back down to 3. Then you subtract 1 more, so that's 2. Okay, so that's it. Now, what's the derivative? So remember, this is my function, right? The table we just filled out is this function, f of x, and it's listed up here, equals 0 to x of f of t, and this is the f of t, right? We just did this thing. This is what we just filled out. That's what this table is. Now, what is f prime of x? F prime of x is just f of x. And so this is the function, f of x. Okay, now, so at x equals 0, the y value is 1. At x equals 1, the y value is 3. At x equals 2, the y value is 3. At x equals 3, the y value is 0. At x equals 4, the y value is negative 4, 0, 1, 6.5 is 0, 7 is negative 1, 8 is negative 1. All right, that's it. What subinterval is f is increasing? F increasing. So remember, this is the derivative, right? This is the derivative. This is f prime of x. So when is this positive? So from 0 to 3. and from, was that 3, 4, 5 to 6.5. Yeah, that's it. That's when it's increasing. Because f prime of x, which is f of x, is positive. Oops, sorry, you could, wow, it froze. There you go. All right. So what was the justification? F is increasing there, so this is increasing. Decreasing, look at where it's below the x-axis. So here, was that 3 to 5? It's decreasing from 3 to 5, and 6.5 to 8. Because f prime of x, which is little f of x, is less than 0. All right? Where in the interval does f achieve a minimum or maximum value? So remember, minimum value occurs when you go from negative to positive. So at x equals 1, 2, 3, 4, 5. At x equals 5, there is a min of, and remember, we can use that table up here, min of 2.5. 2.5. Is there another min? Mins occur at negative, when it goes from negative to positive. There's no other place where it goes from negative to positive. So you have a max when it goes from positive to negative. So there's 2 of them. Okay, so at x equals 3 and x equals 6.5. So at x equals 3, there is a max of, at x equals 3, it was 6.5. So 6.5. And at x equals 6.5, there is a max of 3 1/4. All right, that's D. And then E, find the concavity of f and any inflection points. So concavity, it's concave up when the function, when the slope is increasing. So it's increasing from 0 to 1, and from, what is this, 4, 1, 2, 3, 4, 4 to 6. So 0 to 1 and 4 to 6. All right, so it's concave up from 0 to 1 and 4 to 6. It's concave down from, concave down, so it's what, 1, 2, no, that's 2, 2, 3, 4, 2 to 4, 2 to 4, and this is what? That's 4, 5, 6, 6 to 7. 6 to 7. All right. Justify my answer. F prime of x, which is f of x, is decreasing or increasing. When it's increasing, it's concave up. When it's decreasing, it's concave down. All right, and any points of inflection. So there are points of inflection. So we're not going to count this kind of thing a point of inflection. You could argue that x equals 1 or x equals 2 points of inflection. But we are going to definitely say 1, 2, 3, 4 at x equals 4 is a point of inflection, and x equals 6 a point of inflection. So my POIs are at POIs at x equals 4 and 6. Remember, this is for E, not F, because the f prime of x reaches an extrema. All right, sketch the graph. You just plot the points. So 0, 0, and then 1, it's at 2, 1, it's at 2, 2, it's at 5, 1, 2, 3, 4, 5, and then 3, it's at 6.5, 1, 2, 3, 4, 5, 6.5, and 4, it's 4.5, that's 6, 5, 4, 4.5, 5, it's 2.5, 1, 2.5, then it's 6 at 3, 6.25, then 7 is at 3, 8 is at 2. So there's our graph. Okay. Good enough. All right. That's it. That was today's lesson. Good night.